it is my pleasure to introduce Bruno Loff in this CIMcolloquium of this year. So Bruno is a mathematician, both a mathematician and a computer scientist, and he has recently, I mean, like 1 year ago, earned this ERC grant, and it's so it's these very selective grants from the European Research Council, and we are very happy to have him as a researcher in Lisbon. So a little bit, I'm going to say a little bit about his career. He did the undergraduate and the master's degree in computer science and software engineering at the Instituto Superior Técnico, and he, with an FCT fellowship, did his PhD in the University of Amsterdam under the supervision of Harry Berman on computational complexity, and this was in 2014. Then he had 2 postdocs, one in Prague, one in Porto, and he then he had this opportunity to have this, I mean, to come to Lisbon with his ERC grant, and he's now developing a group on computational complexity in the research center in the Faculty of Sciences called LASIG, and he's also a collaborator of my research center, CMAF-CO. So I knew Bruno, you know, I met with him occasionally when I was a professor in Técnico and he was a master student in Técnico, and so it's a great pleasure to have him as our newest colleague in the math department of the Faculty of Sciences of the University of Lisbon. And by the way, I interviewed Bruno for this bulletin of CIM of this year, and I welcome everybody to read this interview, to know more about Bruno's career and his interests. And so I think that's it. So I pass the word to Bruno. Thank you very much for being able to give this colloquium.
Hello, guys. So we planned this so that you can unmute yourselves if you have any question or comment or want to interrupt me for any reason. Feel free to do so. I've prepared this. I gave this talk once before in the department's colloquium, and I decided to reuse it because I have a bit of an agenda with the talk, which is I would like to convince you that the fundamental questions in my field, although it's something between mathematics and computer science, they are actually very deep and important mathematical questions. And for this, I thought of, so this was my agenda. So what am I going to do? What am I going to say? And I would like to essentially argue that the fundamental question in my field stretches all the way back to Leibniz, who was probably a very interesting person, and I would have liked to have met him because he had thoughts that were so far ahead of his time, as I hope to convince you. So I've also prepared this talk as a read talk, which is a bit unusual, but it allowed, it gives it maybe a more historical, philosophical tone. In philosophy, apparently they always read their talks. I hope, but I hope I made a good story. So I hope you are entertained, and if you have any question or any comment or anything you want to ask, do just unmute yourself and ask away. Okay, so the talk is entitled "Killing Leibniz's Dream," which is a bit provocative, but I think it's actually quite accurate. So that would be the ultimate goal of my field, is to kill his dream. So let me tell you a bit about Leibniz's dream. So Gottfried Leibniz was a German mathematician, and he is most famous for inventing calculus. That's probably why you know him. And he did this almost simultaneously and independently of Isaac Newton, which you probably know. One of the many things that Leibniz did was to build mechanical calculators. So these are machines with cogs and wheels that could automate some arithmetical tasks. And here in the picture, you have an example of one such machine built by Leibniz. His understanding of mechanical calculations led Leibniz to dream. He wondered if it could one day be possible to define a universal language of sorts, which he speculatively called characteristica universalis, such that any mathematical concept could be expressed in this language. Actually, his ambitions extended beyond mathematics. He wanted some kind of language where he could express, God's truth or something like that. But he didn't stop there, so he dreamt further. He wondered whether this universal language, together with this universal language, one could devise a method which he speculatively called calculus ratiocinator, so reasoning calculus, and this method should automate thinking. The method would allow one to manipulate symbols in the language, very much like algorithms for addition and multiplication manipulate Arabic numerals. And by carrying out the method, one could mechanically determine the truth or falsity of any mathematical statement. Eventually, Leibniz hoped that it might even be possible to build a machine that would implement this method, much in the same way that he himself built machines that did various mathematical tasks, usually arithmetic tasks. The machine would then be a kind of mechanical truth oracle. You could ask a question, you'd write it in his language, right? And you'd feed it into the machine somehow, you'd rotate some cogs, and out comes the answer, yes or no. So that's what he would. Now, I will not say much about the foundations of mathematics because I'm not a logician. In brief, there was a search for a rigorously defined language in which to express mathematical statements and mathematical proofs. In the early 1800s, Gottlob Frege devised a formal language which he called Begriffsschrift. I'm not sure if I'm pronouncing that well, but this is roughly translated as a system for writing concepts. And from what I could understand, Frege, by reading a bit about the history, Frege was inspired by Leibniz, so by his characteristica universalis idea, and was trying to construct a language for mathematics based on logic, which at the time was very radical. But for superficial differences, so this is a proof written in this Begriffsschrift, and of course it's a 2D script and it's some kind of weird thing, but this is all superficial. Really what he has invented is what we know today as first-order logic. Eventually, mathematicians at the time came to see first-order logic as the appropriate choice of language in which to express mathematical statements. Frege's unequivocal syntax, together with simple inference rules such as modus ponens and reasoning by generalization, could apparently be used to express all the mathematics that was known at the time. And as far as I'm aware, this is still true. So essentially, all of mathematics can be expressed using first-order logic, although a friend who does, a friend says that when you go to category theory, it's kind of unnatural to do this and so on, but we know no proof today that cannot be expressed using first-order logic, modus ponens, and generalization. So at the time when this was discovered, this is kind of a very radical and important thing, and there were three outstanding issues that remain. The first is the issue of consistency. Can we provide some reasonable choice of axioms from which we can derive all known mathematics and for which we can prove that these axioms will not lead to a contradiction? The second is the issue of completeness. Can we provide such a consistent choice of axioms such that these axioms can always prove every statement or its negation? And the third issue was decidability. Can we devise a method like Leibniz wanted that would allow us to determine the truth or falsity of a certain statement by some kind of calculating procedure? More precisely, is there a calculating procedure which, when we write a proposition in first-order logic, determines whether or not the proposition can be proven using the usual logical rules of modus ponens and generalization. Right? So this was kind of the question that was a hot question in 1900, so 1900. And indeed, these first two problems of consistency and completeness were first proposed by David Hilbert, that's him, in 1900 at the International Congress of Mathematics. And the third problem of decidability was proposed in 1928 by Hilbert and his PhD student, Wilhelm Ackermann, at an international conference in Vienna. The status quo in Hilbert's mind, circa 1930, was that all these issues would one day be resolved. Right. Okay. So now I'm trying to get into Hilbert's mind, and it was such a visionary idea. So Hilbert's research program aimed to provide a system of axioms that were expressive enough to derive all mathematics. That's what he wanted. And furthermore, he wanted to prove, he wanted to do this even using just a small subset of these axioms, that the system is consistent, everything it proves is correct, and complete, meaning anything can be proven or disproven using this amazing system. Now, if Hilbert's program had succeeded, then all of mathematics would be perfectly described by a finite description, right? I write the axioms in a page, bam, all of mathematics follows from there. So just imagine what that would be like. I cannot imagine anything else that would better fit the description of a holy book. A consistent, complete system of axioms would really be like a Bible of sorts, containing God's very own truth, completely written down in a finite number of sentences. The decidability procedure that Hilbert would like was just the cherry on the top of the cake. If a complete and consistent system of mathematical foundations would be the gospel, then a concrete, finitely describable procedure to decide if something was true or false, that would be like the praxis of his religion. With sufficient devotion and persistence, by counting some kind of beads and some kind of mathematical rosary, right? You take the sentence and you turn some lever and you do some procedure. In the end, you could arrive at God's answer to any question that you would ask, at least any mathematical question. This vision was so tantalizing for Hilbert that he, like Leibniz, worked for many decades to bring this vision into fruition. In fact, this is the gravestone of Hilbert, and in his gravestone we can still read the words, "Wir müssen wissen, wir werden wissen," which translates roughly as, "We must know, we shall know." So that was Hilbert's vision. However, in 1931, a young Kurt Gödel arrived on the scene and Hilbert's program came crashing down. Gödel showed that no sufficiently expressive, consistent system of axioms is complete. And in fact, no consistent system of axioms can prove its own consistency. Now, so this is all logic so far. They wanted to kind of formalize mathematics in a finite way, and apparently you can't do it actually. And that was what Gödel showed. And then Turing arrived on the scene. This is Turing. Having learned of Hilbert's program and Gödel's negative answer to the first two problems of consistency and completeness, Alan Turing, a young and unknown mathematician, started thinking of how he might prove that the third problem also had no solution. So, imagine the situation, right? So, okay, so we don't have a system of axioms that can capture all of mathematics, but we do have systems of axioms. They're very expressive. I can still ask, is there some kind of algorithm that I give you a sentence in first order logic, and the algorithm should say, yes, it follows from these axioms, or no, it doesn't, right? So that would still be possible, right? So Now, Turing thought that in order to give a negative answer to this question, one must first have a precise definition of what a calculating procedure is. Only with a mathematically precise notion of what a calculating procedure is can one hope to rigorously prove that no such procedure exists. And this would solve Hilbert and Ackermann's decision problem. But now we have to put ourselves in the heads of someone from 1933, let's say. Like, what hope is there really to define such a thing precisely? Of course, now we know that it can be done, right? There's a definition, mathematical definition of an algorithm, of a calculating procedure. But let's think from the point of view of someone living in the early 20th century. What hope is there really of rigorously defining the notion of a calculating procedure? And I'd like to make the argument that there should really be no hope. Like, place yourself in the early 1900s. As of today, mathematicians have been doing calculations for tens of thousands of years. Tens of thousands of years. In order to do these calculations, very intelligent mathematicians, including some of the greatest geniuses that have ever lived, have invented thousands of calculating procedures of varying degrees of sophistication. Hundreds of these calculating procedures are in use just today, hundreds of different procedures. Some of these calculating procedures are extremely sophisticated, including infinitesimal and integral calculus, numerous methods for numerical approximations, some calculating procedures that can even predict the movement of the planets in the sky. And some of these procedures are done with the aid of various utensils, right? And such as the abacus, ruler and compass, mechanical computers of various kinds. For example, the census in the United States, the census of 1890 was done using machines. And what you are asking to someone in this early 20th century is for a single magical definition, which somehow can encompass all of the above methods, all of these sophisticated procedures in one definition. And this definition of of an algorithm or of a calculating procedure should not just capture any method that's known at the time, but any future method, right? So there's a picture of aliens, imagine. So aliens will come in the future, come up with a method. It has to be captured by your definition. Now, what are the odds, really, that such a definition even exists from the perspective of someone who doesn't know it, right? Only someone naive in the extreme could hope for such a definition. So let me tell you an anecdote on the naivety of Alan Turing. It goes more or less like this. So the Second World War is just around the corner. It's 1930 something. In the United Kingdom, an armed citizen militia was created called the Home Guard. Here is a photo of the Home Guard. Citizens would be encouraged to join this militia. You know, the idea would be that it would help protect against potential German invasion. So Turing decided he wanted to learn how to shoot a rifle. So he filled the required paperwork to join the Home Guard. He joined and he took the freely offered shooting lessons. After Turing had learned how to shoot a rifle, and apparently he became quite the marksman, he grew bored with the Home Guard and their rallies and whatnot, and he stopped attending the various events that the Home Guard organized. In noticing that Turing had stopped participating in the Home Guard military parades, a military officer, threatened him with repercussions. The officer claimed that by joining the Home Guard, Turing was subject to military law, and Turing insisted that he was not, that this had not happened. Their disagreement comes because of the following. So apparently, when you sign up for the Home Guard at the time, there's a question in the form that you have to fill. And the question says, do you understand that by enrolling in the Home Guard, you place yourself liable to military law? And the general or whatever captain that knew that Turing had filled this form, and so he believed that Turing was liable under military law. But it turns out that under this question, Turing wrote, no. He just said, no, I don't understand this. So, of course, I'm not liable under military law. Of course, one should say that, far from dodging the draft, during the war, Turing led the team that broke the Nazis' encryption and saved thousands of lives, and possibly without his help, the Allies would have lost the war. He was also later persecuted by the government for being gay, but that's another story that was told in other places better. Okay. So in his naivety, Turing tackled Hilbert's decision problem. For this, he had to find a precise definition of a calculating procedure. So what he did was that he mentally analyzed what happens when someone engages in the act of doing a calculation, as many mathematicians have done over millennia. And in doing so, Turing invented the computer. So I've written a paper on this in the bulletin of this SPM. And in section 9 of Turing's paper, you will find the most brilliant piece of written science that I have ever read. Turing analyzes an act which can be as complex and seemingly ill-defined as that of a human being doing a calculation. There's all these strange things going into a calculation, right? So how experienced is the human in this particular method of calculation? How experienced is he in doing calculations in general? Is this human dumb? Is this human intelligent? Did he have a cup of coffee? Is he tired? Is he using a board, a pen, a pencil, a compass, what? But in Turing's analysis, he distinguished that which is essential to the act, and he discards that which is superfluous, to the point that his analysis can finally be distilled into a mathematically precise definition. And after doing so, after giving a rigorous formal definition of algorithm, Turing proceeded to show that one can, in principle, build a universal machine which is capable of carrying out any calculation. So he didn't just understand what the calculation was, he understood that there was some kind of universal method that could carry out any calculation. And by any, we mean from the simple arithmetic of the Egyptians to the latest methods for predicting the position of Jupiter in the sky. Any calculation that can be made, any calculation that has ever been made by any mathematician in the past, or any calculation that will be made in the future, Turing's universal machine can make it. So he invented the computer. And the computer is the most mathematical of all human-made objects. And we all carry a computer in our pockets. By the way, a lesser-known fact is that Turing also invented the neural network, which is the computational unit on which current artificial intelligence is built, and which will change our lives in the 21st century at least as much as the computer has done in the 20th century. For the better or worse, that remains to be seen. After inventing the computer, Turing had a rigorous mathematical definition of what a calculating procedure is, and then he was able to show that there exists no calculating procedure for deciding whether a given statement is provable. Okay, so I give you a first-order logic statement. You want to know if it's provable from some axioms or not. Turns out that there's no algorithm that does that. And by doing so, Turing essentially solved Hilbert's decision problem. So Turing showed that there's no method which I give you some axioms, a first-order sentence, and the method is supposed to say, yes, decidable, yes, the sentence follows from the axioms, or no, it doesn't. And Turing showed that there's no method. So it seems that Turing has killed the dream of Leibniz, right? So that there is no method for deciding if a sentence is true or not. But did he? So let's talk about the length of proofs a little bit. So Turing showed the following. There does not exist an algorithm which, when given a predicate phi written using first-order logic, can decide whether or not phi is provable, let's say from some axioms. And this seems to kill Leibniz's dream. It seems to say that there is no calculus ratiocinator. However, the following problem obviously has an algorithm. Suppose we're given a statement. So there does exist an algorithm. Now we're given a predicate phi written in first-order logic and the natural number n. There is an algorithm that can decide whether or not phi is provable by a proof of length at most n. Namely, I enumerate every single proof of length at most n, they're finitely many. For each of proof that I've enumerated, I try to check if the proof is a correct logical deduction of phi. And if it is, then I say, yes, there's a proof of length at most n. And if after going over all proofs, I see that there isn't one, then I conclude, well, there's no proof of length n. So that's an algorithm. So what's the problem with this algorithm? And the problem is parabor. So this is what the Russians call it. It's the problem of exhaustive search. The issue, of course, is that the above algorithm simply takes too long. Enumerating all proofs of a certain length n one at a time takes time which is exponential in n. For even small n, actually running the algorithm will require more time than the lifetime of our universe. So the question naturally arises, is there an efficient algorithm which, when given a statement phi and a number n, either finds a proof of length at most n, if such a proof exists, or says that no such proof exists if that is the case? That we know, Kurt Gödel was the first person to ask this question. Here's an excerpt from a letter of Gödel to von Neumann, 1956, written in 1956. So 20 years after the invention of the computer, 10 years after the World War, roughly. He asks the following. Von Neumann was ill, he had cancer, but Gödel didn't care. He just sent him a letter about mathematics anyway. And he asks the following. Suppose, von Neumann, if there really were a machine for solving this problem of deciding whether there's a short proof or not, a proof of length at most length. Now, suppose there wasn't really a machine where the running time of the machine was at, approximately k times n, or even k times n squared for some constant k. Then this would have consequences of the greatest importance. Namely, it would obviously mean that in spite of the undecidability of Hilbert's decision problem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. After all, one would simply have to choose the natural number n so large that when a machine does not deliver a result, it makes no sense to think more about the problem. Now, it seems to me, however, to be completely within the realm of possibility that the complexity of solving this problem grows that slowly, meaning linearly or quadratically in the length of the proof. So this is Kurt Gödel at around that time. And of course, one may generalize Gödel's question, right? So is there an algorithm for finding if there's a proof of length at most n that runs in time n to the c for some constant c? And now Gödel wasn't the only person in the 50s that was kind of interested in this type of question. For example, in 1955, John Nash wrote a letter to the CIA suggesting that perhaps cracking a cryptographic code would require an exponential time in the length of the cryptographic key. On the other side of the Iron Curtain, Soviet mathematicians were also already concerned with this problem. So take a look at the clock to make sure. Yes. So right, so in Soviet Republic, people were interested in the following problem. So I give you some kind of function, some kind of, I give you a description of some functionality that you'd like to implement as an algorithm, and you're trying to find the most efficient algorithm that would implement this functionality. And these questions are all related, actually. The question of breaking a code, the question of finding an optimal algorithm, and the question of solving proofs, they have some relation, and we understand more or less this relation. Even though, even recently, there have been developments there. Okay, so let me tell you a bit then about computational complexity. So while the first questions about the efficiency of algorithms started being asked in the 50s, it was only in the 60s that this understanding became clear enough to be articulated into precise mathematical definitions. In 1965, Joris Hartmanis and Richard Stearns published their foundational paper on the computational complexity of algorithms, where they first defined the notion of a computational complexity class. So Each computational problem usually comes with a natural measure of input size. So think of a computational problem. So for instance, if I want to multiply two numbers, the number of digits in the numbers would be the length or the size of the input. If I want to multiply two matrices, then the size of the matrices would be n by n, maybe. If I have a graph on n vertices, the complexity would be n. If I have a first order logic sentence with n symbols, then n would be a reasonable notion of input size, etc. Now, when we think of devising algorithms for computational problems, we expect that the required resources that the algorithm takes, such as the time taken, will necessarily grow with the input size, right? Because more length means more complicated problems. An optimal algorithm is one which uses the fewest resources possible for each input size. The computational complexity of a problem is the amount of resources, say the amount of time, used by the best possible algorithm, by the most efficient algorithm. Let me give maybe a concrete example. So think of multiplication, right? So you want to multiply two n-bit numbers or n-digit numbers. Now we've all, like the first thing that we learned in mathematics was how to sum. We sum two numbers. We write the digits right one on top of each other, and then we scan from right to left, and we kind of remember sum, and we copy, and in the end, so how much time does it take? This simple algorithm that we learned in high school. It takes time about n. Right? Because I have to scan essentially n digits, and each digit costs me a unit of time. How about the algorithm that we learned for multiplication? Right? So what do? We write the two numbers, one on top of the other, and we scan from left to right. But now, or from right to left. But now there's an issue, right? Because for each digit on the bottom number, I have to scan the top number completely to multiply it by that digit, right? And then I copy the outcome, and then I go to the second digit, and I have to scan the top thing again. So if I have two n-digit numbers and I want to multiply them, the algorithm that we learned in school takes time roughly n squared, right? And Kolmogorov in the 50s had this seminar going on and saying, I think that you can't possibly do better. So that's 1900. So by 1900s, no better algorithm was known. And Kolmogorov went like, nah, you can't do better than this. And he started a seminar just to try and show that you can't do better than n squared to multiply two numbers. And within 3 sessions, famously, the seminar ended because one of his students proved that there was a better algorithm, that instead of taking time n squared, it took time n to the 1.63 or something like this. So it's not really obvious often what the best algorithm is for something. And nowadays, we know that multiplication of two n-bit numbers can be done in time n log n, which is almost as fast as addition. And that's really highly non-trivial if you really think about it. Okay. Okay. So, right. So there's two kind of results here in the computational complexity, and we call them upper bounds and lower bounds. So upper bounds are like you want to prove that the complexity is at most something. So if you want to prove upper bounds, you have to find better and better algorithms. And there's another kind of result which we call lower bounds, which are results of the kind you can't do better than this. So there's no algorithm that can do better than this, right? Gödel's question really is then asking whether for a lower bound. He's asking whether there is a, let's say, polynomial time algorithm to decide whether a first order sentence follows from certain given axioms. And of course, if there is such an efficient algorithm for this, we can all be fired because we can just hire a computer. That might still happen anyway, but by a very different approach. Okay, so right. So now, but there's this other kind of fundamental result in my area, which is called completeness. And right, so there's a way in complexity theory of formalizing the notion that one problem is harder than the other, and this is what we call a reduction. And the way we do it is we suppose by hypothesis, for example, that we have an algorithm for solving a certain problem B. Now, if under this assumption, we can somehow get an algorithm for A. So maybe we, to solve some problem A, we make some calls. We suppose that we could solve problem B, and we somehow try to solve problem A using this imagined solution, right? So maybe we make some calls to an oracle, we call it an oracle, that would solve problem B. And then we have shown that problem A is no harder than problem B. So the complexity of A is at most the complexity of B. And what turns out to happen is that by using these notions of reductions, which are not obvious, and so this notion was invented in the 60s, essentially by these two fellows, one on each side of the Iron Curtain, is that using this notion of, the complexity of an algorithm of a problem is at most the complexity of another problem, we have some kind of partial order, right? And now we can collapse the partial order, right? So we put together all the problems that have similar complexity. And what these two guys have shown is that there are problems that there's single problems that characterize entire classes of problems. Meaning, you can reasonably define a class of problems. One of them would be, for example, the class of all problems that can be solved in polynomial time. That would be P. We call this class P. And there's another notion of a class of problem, which is the class of problems whose solution can be efficiently recognized, right? So think of this, like I give you a Sudoku puzzle, right? So it's a partially filled Sudoku puzzle, or it's easy. If I give you an answer to the Sudoku puzzle, it's easy to recognize, right? All you have to do is check if all the rows and columns, it's a simple check, right? Or for instance, if I give you a proof, it's easy to check that it's a valid proof. I just have to go over every line of the proof and check. So all of these problems are in NP because the solutions are easy to recognize. But how about finding such a solution? Is that also easy, right? And what Gödel was asking was essentially this, right? He was asking, I can easily recognize a valid proof if I'm given one, so can I easily find a valid proof if one exists? Right? And that is the P versus NP question. That's the P versus NP question. Right. So, so let me recap. So there's this theorem, and this is proven by Turing. There does not exist an algorithm which, when given a predicate phi written using first-order logic, can decide whether or not phi is provable. But there does exist an algorithm which, given a predicate phi and a natural number n, can decide whether or not phi is provable by a proof of length at most n. But this algorithm runs in exponential time because it essentially searches the algorithms we know, at least have to search essentially all proofs. And now the P versus NP problem asks, does there exist an efficient algorithm which can solve this question? Let's say I wanted to run in time polynomial in the length of the statement. And what complexity theory comes and say is that this question, which was first asked by Gödel, actually is equivalent to any number, to a large number of similar questions. So there's these computational complexity classes, which so this problem is just as hard as solving Sudoku puzzles, for example. Which would mean, for example, that I could encode any mathematical question as a Sudoku puzzle, which is really somehow not obvious. Right. So let me kind of, so I guess what I'm trying to argue here is that this question goes way back. It goes all the way back to Leibniz. And it's somehow fundamental. It was first asked by Gödel. And so let me tell you kind of an overview of essentially what happened and why we're stuck, which is kind of the fact. So I've told you about this, right? So there's some invention of the computer in the 1930s, and then Gödel asks this question in the 1950s. We have the first formal definitions of that kind of explain, categorize all these problems in the 60s, and then the notion of NP completeness is invented. And then in the 1980s, what happened was that many people tried to prove that, they tried to prove that P is not equal to NP by doing some kind of diagonalization. And they tried and they tried and they tried and failed. And then these three guys, Baker, Gill, and Solovay, came along and they gave us a good reason why you can never hope, no matter how smart you are, to prove this by some kind of diagonalization trick. So why were people trying this trick? Because, Turing's proof, Gödel's proof, they were all using this trick of diagonalization. And so it's natural to try and kind of port this version into this question. But it turns out that there's this barrier result. It's some kind of independence result. It says that any attempted proof that P is not equal to NP cannot have this feature, which is that it relativizes. And then you look at essentially all the proofs that were known at the time, and they all have this feature that they relativize. So it's some kind of partial independence result. Okay, but people didn't give up in the 1980s, and then so in early, starting mid 80s, early 90s, they started approaching these combinatorial techniques, which are techniques for proving lower bounds, where you try to analyze the algorithm as some kind of combinatorial object. So, instead of thinking about Turing machines, you start thinking about circuits. And what a circuit is a graph. So maybe there's some kind of combinatorial property of graphs that we can use to try and prove lower bounds. And this has been somewhat successful, especially like one of the most famous results is by Razborov, who is maybe the most towering figure in my field. And he has shown that, if you have circuits, but you can't do negations, essentially P is not equal to NP. So in that world, monotone world where negations don't exist, P is not equal to NP. And he has proven this using some kind of smart combinatorics. It's highly non-trivial proof. But very interesting. And then people were, their hopes were up, and they wondered, okay, so very soon we're going to solve the P versus NP problem, because we solved it in this monotone case where there are no negations using these fancy combinatorial techniques. And so we're going to be able to do it very soon. And of course, Razborov, being the person he is, he thought a lot about the problem, and I seem to have somehow lost my slides. Oh, let me try this. Okay, good. And he came up with another barrier, which is called the natural proofs barrier. And it essentially says the following. It's also kind of partial independence result. And it says that, so you again analyze what's happening in the proofs that we know. And the proofs that we know, when you try to prove that a function has no algorithms, you usually use some property of this function. And in some sense, you're trying to distinguish the class of easy functions, and you're trying to prove that you have a function that's outside of this class. And for this, you're going to use some property of the function, because your proof says something about your special function. And so whatever it says about the special function is part of the proof. So usually, in fact, it turns out always so far, or almost always, when you have a proof of a lower bound, that there's this problem that has no algorithms, you can extract from it some property of the hard function that you've proven. But usually this property that you can extract from it has a number of features, and which you can enumerate. And any proof from which you can extract such a property, we call it a natural proof. And I'm not going to get technical, so I'm not going to say it is. Let's just say it's very hard to avoid these features whenever you build a proof. So somehow, let's say, I think it's fair to say that essentially any constructive proof, any attempted proof that P is not equal to NP, which is reasonably constructive, will be a natural proof. However, there is this result by Razborov saying that under reasonable assumptions, no proof that P is not equal to NP can be a natural proof. So essentially it says that there's no constructive proof that P is not equal to NP. And in some sense, there's some attempts at formalizing that. But I think that you don't have to. I think that you just read this paper, you'll kind of grasp something out of what this notion of constructive is. And that this certain notion of constructivity, no constructive proof can prove that P is not equal to NP. And now, essentially, in terms of lower bounds of what we can prove and can't prove, this is still the outstanding barrier. So the proof will essentially say that if you have a computational model where you can, I don't know if any of you have programmed, but somehow when you program, sometimes you want some random bits and you call a pseudorandom generator. Again, random, there's this function in C, random, open parenthesis, close parenthesis, and it gives you a random number. It's not really random number, right? It makes some fuzzy calculation, it gives you some number. But because the calculation is kind of sophisticated, you expect that you can't really predict, and so that should be good enough. So this is called a pseudorandom generator, a number, like a procedure that gives you kind of a number that looks random. It's called a pseudorandom generator. And there's reason to believe that there truly exist pseudorandom generators that work as well as real randomness. But if that's true, then the natural proofs barrier. So it's under that condition that you have this barrier. So but this also means that if you have a notion of algorithm which is complicated enough to generate pseudorandom things, then the natural proofs barrier applies, and you're not going to be able to prove lower bounds for this. And such, I mean, P is like a very powerful class. We have much less powerful notion of algorithms that already have pseudorandom generators, and so this natural proofs barrier applies not just to the P versus NP problem, but even for problems that are much lower in the hierarchy of complexity. So, so what has the field done since 1994? Well, I'd say like one of the most interesting developments was the development of communication complexity, where you can prove lower bounds, and it's kind of a frontier there. This communication complexity can kind of cover the frontier before which the natural proofs barrier appears. There's, for instance, several interesting results on the length of proofs. So we can actually prove lower bounds on lengths of proofs in certain systems of logic. The randomization is maybe a bit complicated to explain, but for instance, we've developed this notion called probabilistically checkable proofs, right? So right now, when someone gives you a paper and it has 100 pages, to check that the paper is correct, you have to read all 100 pages. But it turns out, and this is just true, there's a notion of proof, which is such, so in principle, we could have encoded the proof in this paper in such a way that for you to be convinced that is correct, you'd throw a coin into the air a few times and you'd look on 100 positions. And on these 100 positions, you do some tiny calculation. And if all these checks that you've done have passed, then you are confident with 99% probability that the proof is a good proof. So that's probabilistically checkable proofs. There's some kind of in proximity results. Oh, there's zero knowledge proofs, which is also fun. So, suppose that someone you want to convince someone that something is true without revealing anything else. So, for instance, I don't know if you know like crypto coins, but so in crypto coins, how do they work, right? You have Bitcoin, and so essentially works because there's a public ledger that says how much money does anyone have, right? So the amount of money that anyone has is written in this public thing in the sky, and so if someone says, okay, I want to transfer 5 euros to person B, you can check that this transfer is valid because you go into the transcript that is in the sky and you check if the person really had 5 euros. And then if she did, now you subtract 5 from your mental transcript and you add 5 to the other account, and now everything is good. But this is public. Now suppose you want private. You want to maintain such a system, but without knowing how much money anyone has. How do you do that? Actually. So then the task of someone who wants to transfer money is to convince to other people that they have transferred some amount of money to someone and that they could do that, right? That they could do that. They had enough money, so they transferred 5 euros to someone, and that they could do that, but they don't want to say to whom that was. They don't want anyone to know to whom they transferred. They don't want anyone to know how much money they have. So the only thing that anyone should know is that this was a valid transaction. And now how do you do that, actually? So you do this using the so-called zero knowledge proof, which is a proof that some statement is true. The statement here would be the transaction is valid. It proves that the statement is true without revealing anything else. And it turns out that these things exist, at least for simple arithmetic tasks like, keeping the books. You can do this. Of course, quantum computing, I mean, there's a lot of things in the field. But I guess I can kind of stop now. And if you're interested in kind of the historic part, there's this book, Engines of Logic, Martin Davis, which does a good job of explaining the story. There's this survey. I mean, often the Soviets are neglected, and they really shouldn't, because their school is just amazing. So there's this kind of survey by Trachtenbrot about what was happening in the Soviet Union, something by Leonard Levin, and this blog is also kind of a nice blog to follow if you care about these questions. And I guess I have nothing else to say.
Okay, thank you very much, Bruno.
Yeah, thanks.
So are there any questions about this?
I have. Hello.
Yeah. Please.
Yes, just let me put the camera on. Hey, thank you so much for this really nice and inspiring talk. On your previous slide, I was reading in the end quantum computing, and I was really, since the middle of this talk, thinking about that. Is that going to be a game changer, quantum computing, because the algorithms are not based on 0-1? And I felt a bit disappointed when you jumped this last part. Can you tell us something about that?
Sure. So what happens? So a quantum algorithm, so sometimes people think that a quantum algorithm, because you have so-called superpositions, then a quantum algorithm is going to be able to try everything at once, right? But a quantum algorithm is more like a probabilistic algorithm. So you shouldn't think of the superpositions literally, like you're trying everything at once literally. Much in the same way, like if you have a randomized algorithm, right? What are you doing? You're tossing a few coins, right? And depending on the outcome of the coin, you do different things, right? So you could say that in some sense, you're trying everything at once. I mean, so when you analyze, right? So now you try to analyze all of the runs of the algorithm all at once, right? So there you'll have some probability distribution over, you also have some probability distribution over the possible states in the memory of your algorithm, right? And if you look at this probability distribution, you can say, well, maybe I'm trying all these things at once, but you know that you really aren't, right? You tossed a few coins and the algorithm can only do one of the paths. And our quantum algorithms are the same, except instead of being L1, like instead of being probability distributions, you have, instead of having the convex combinations, you have the one sphere. So now actually probabilities can be negative and they kind of can cancel each other, which is kind of surprising. But I think it makes more sense to think of quantum computing as some kind of probabilistic algorithm than some kind of algorithm that tries everything all at once. And whether they will make a difference, it depends on whether people can build these quantum computers, and they've been trying for a long time, and so far not really successfully. But the thing is that if you want to understand like particles and molecules and things, they are running in this kind of probabilistic way, this with negative probabilities, and so if you want to simulate these things, you need that power. You need and if tomorrow there came a quantum algorithm, a quantum computer, it just works fine, it's great, it does everything, then that would make a big difference, because you could essentially put any molecule that you want and simulate it and run it in your computer, right? You could put your entire, whatever, your cell, take a cell and just put it on the computer and press play, and it will simulate the cell perfectly. Of course, we can all see that would be quite useful if you want to make anything, medication, chemistry, anything. So yes, so if there was a quantum computer, if we can manage to get that noise level down, and it will be useful in maybe chemistry and biology at some point. Yeah, but it's unclear. But I mean, AI is suddenly so surprisingly powerful all of a sudden. So maybe they will be. I don't know. We'll see.
Okay,
But
thank you.
Yeah.
More questions, comments, or thoughts? Samuel?
Oh, hi. So I'm not sure if my mic working?
Yes.
Can you hear me? Okay, good. Okay. So thanks, Bruno, for the very nice talk. It's very interesting. I have a question, because I was a little bit confused towards the end when you mentioned the combinatorial techniques and the natural proofs barrier. I mean, my question is, I mean, does that mean, for example, that in intuitionistic logic or constructive logic, P versus NP is undecidable, or
Yeah.
is...
Yeah, the thing is that I don't know enough about logic to be able to tell you. So a natural proof is, so you've proven that you have some model, right, of computation, and you've proven that some function cannot be efficiently solved in this model.
Mm-hmm.
Now you look at the proof, right? You're doing logical steps, right? Because f is like this, then da-da-da. Because f is also like that, then da-da-da, right?
Mm-hmm.
So using some property of f, like this, f is like this and f is like that. In your proof, you're using some property of f to come to your conclusions, right? So in principle, if you replace f with any other function that has the same properties, your proof will also go true, right? So let's just extract the properties of f that we're using in the proof, right? It's some property, meaning it's some function that I give you. It's some property, meaning it's some predicate. I give a function to this predicate, and it says, yes, it has these properties that I need to carry out the proof, or no, it doesn't have it, right? Now, here's one aspect what it means. So in a natural proof, this predicate should be efficiently decidable. So a natural proof, it needs another feature, but maybe that's technical. I'll just shove it aside. But one of the features that you have is that the property of f that you use to carry out your proof should be efficiently recognizable. So in a sense, that's a constructivity requirement. It's very semantic constructivity requirement, but it is a constructivity requirement. So in that sense, it's saying something about constructive proofs, right? So you look at your proof of a lower bound and you use some property of f. Now, if I give you the truth table of f, right, I just give you f as a giant object. Can you, in the size of this giant object, polynomial in the length of this giant object, can you decide your property? And what happens is that you go and look at the proofs that we actually do. And almost always, you can somehow, even if the proof originally wasn't constructive, you can, you shift it a little bit. It turns out that you can adapt it and it's constructive. In the sense that the property that you use is recognizable and efficiently. So it's a semantic notion of constructivity. How that exactly relates to model logic and all these things, intuition is that I actually don't know. I'm not a logician, so.
Okay.
Yeah.
Well, thank you. That clarified a few things. Thank you.